Good morning, good afternoon, and good evening, everyone. So today we're going to be talking about how to find roots using various methods in scientific computing. So to start off, well, let's define what a root is. So a root is a function f, and let's say this function f is defined to be some x value. Let's call it x tilde, such that when we plug this in, when we plug in x tilde into our function, it becomes 0. So that's the mathematical definition of it. Um, yeah, so those are roots. And so finding roots is a crucial part of scientific computing. And so given a function f, we can't always easily find a root ourselves. So how will a computer do it? Well, the easiest thing would be to fill in every point into f and seeing if it's equal to 0. So that's a lot of plotting and plugging in, a lot of guessing, and it will probably never give you a root, surprisingly, especially if we have a weird function. So let's say we did find 2 points, right? And these 2 points are, well, let's say XL and R. XL and X sub L and X sub R. So let's say we found, or we found my English. We found 2 points. After doing all of those plotting and plugging in, we're gonna say XL and XR. And we're gonna say XL is less than XR. Such that, well, we're gonna say if we plug this into our function, well, these two functions now have different signs, right? What do we mean by different signs? Well, we mean if f is continuous, then there must be a root in between these 2 points, right? So if f is continuous, well, we're going to say there must be a root, which means there is a root between these two values, right? If we, let's say we make a second guess, right? So let's make a second center guess. So let's say it's the middle. It's the middle. So let's just denote it as x sub c. And how do we get the middle value of xl and xr? Well, of course, we add them. Then we divide them by 2, right? And from there, well, we can again look at the sign, right? So we look at the sign again. Of our function at this point and see with which point x sub L or x sub R it differs. So which one makes it different, right? and determine which point so we have XL and X sub R, it differs, right? Because we're saying they have different signs. So which one is it different from? Is f of x sub c different from the XL point, or is it different from the XR point? And so let's say if our XC and XL have different signs, then the root lies there, right? So here we're analyzing some behavior. If we say that our f of x sub c and our function at xl have different signs, the root is there. Specifically in that interval from XL to XC, right? If not, then it probably lies on the other side. So XL, XR. And this basically cuts the interval in half, in which the root can lie in either both intervals. And we can keep going this, well, we can keep doing this iteratively. So we use our iterative methods to do this until we find the root, right? And so let I be the length of the original interval. So we also have to look at this interval, right? So let's say, oh, and we keep doing this iteratively until we find the root, right? Let's say let I be the interval. Um, the length of that interval. And so after a certain number of iterations, right? Because we're gonna do this finding the root again and again and again and again and again. Then after a certain number of iterations, let's just say P, after some P iterations, then there will be an error. And so that error will be I, multiply it to, this is interesting, multiply it to 2 to the negative P. So that's the error. And this is basically this idea of finding the root again and again and again, and here measuring this error. Well, this is the bisection method. So here, since we know that this is a negative exponent, we're actually, as we keep doing this, our error will get smaller and smaller and smaller and smaller. That's what's happening, right? Our error will become smaller. And so that's the bisection method. Okay. Let me, okay, I'm gonna try doing something a bit different here. I'm gonna try, okay. I'm gonna try doing this in code, right? And I hope it works. 'Cause if it doesn't, then that's too bad. I think it should work though. Let's just hope. I'm gonna do this in MATLAB because my course is being taught in MATLAB. Um, okay. Let me. Okay, why is it not opening? That's fine. I'll just exit. So my thing cannot open. Let's do it again. Or rather, I might just show the code. That's okay. I'm just gonna code it myself. Um, there we go. Nice. I thought it wasn't gonna run. Okay, let me. And I'll just take a screenshot of the code or something. Okay, let me do. Come on, let me open. There's no opening. God, this computer is slow. Okay. Okay. So I'm just gonna run a specific section here. Okay, I'm gonna stop sharing this. I'm gonna go to my MATLAB, and it should work. So in MATLAB, if we were to apply this bisection method, right? So what we're gonna do here, well, we're gonna apply it obviously. So the first thing we want is an XL and an XR, right? So XL, we want to initialize these two things, XL and XR, right? This could be any, to be honest. I'll just go with 3 and 4. It doesn't really matter. Let me go 3, then let me go 4. Then I think I can run the section so that you guys can see. There it is. XL is 3, XR is 4, right? And then from there, okay, let me keep going. I'm gonna compute my center, right? And so my center is XC. Here I'll put some comments. What I did here was initialize my XL and XR. And then the next thing I do is compute for my center, right? And this is XL plus XR. I divide that by 2, right? And so what's that gonna do? Well, if I run this section again, and there we go. 3 plus 4 is 7. 7 divided by 2 is 3.5. So that's what it gave me. Then what's the next thing I'm gonna do? I'm gonna do a while loop, right? So here I want to check. So like I did in my thing here, if we share this again. So what I did here was, okay, I computed for XL and XR, those 2 points. And then, well, I technically didn't compute for them. I just plugged them in. And then, well, I make a center guess. And then I look at my function, right? And then when I determine which of them differ, either XC and XL or XL and XR, which of them differ, and then we keep doing that again and again. So we don't know how long we're going to be doing it, so I'm going to code it up using a while loop. Yeah, those are the interval lengths, and then we're going to multiply that by 2 to the power of negative p iterations. that's what we're gonna do. Let me go back to my code. So let's quickly do that. Well, I don't have a function here, so let me look at this function here. I don't know. I'm just gonna use this. So I have this function. Could be any function, honestly. Okay, let me also put that function here, and then let me run it again. Okay. That function's if I write it, that's basically f of x equals x minus x minus pi all the way to the power of 3. That's basically what that is. Okay, so here I'm going to what I say? Oh yeah, I'm gonna compute for I'm gonna do that iterating process again and again, right? I'm gonna do the iterate again and again. So this is going to be some while loop. So while my function. So let me see. Oh yeah. I'm gonna do it for a certain number of times. Maybe I also need to look at that. So P, right? We're gonna do P. Let's say 100 times. Not sure. I'm gonna do it, let's say from my index 1, starting from 1 all the way to P. I think that was how they did it. Yeah. And then I put my functions here, my fxl and fxr, my xc, put that as well in that function, and then do my else. It's actually a for loop, my bad. It's funny how they put a while loop there. Okay, let me just do, actually, you know what? Let me just run this part. Yeah, I'll just run this part. So the idea here is we get this XL value, we get this XR, we have this particular function, we have n equals 44. We do it all the way to n iterations. We put these in a function. We have our center. We put that as well in a function. And if we multiply my XL times my XC, and it's less than 0, then we reassign my XR to XC, right? And else if I do FXR times FXC, well, and it's less than 0, well, now I'm going to do that. I'm going to reassign my center to my XL. And I'm going to do that again and again for 44 times. But if none of these work, then there is no shifting in the signs, right? There's another process of us doing that again and again. Let's run this section. Let me see what it does. Did we get anything? Okay, I don't think it's outputting anything. Let me do this so that we can see the shifting. I want to see that shifting. There we go. So here, XR and XL, or actually my XR is going down. from 3.5 to 3.25, my XL is going up. My XR is again going down. XL is going up. XR is going down. XL is going up until we reach the end. And we see here my XL and my XR reached 3.1416, right? And so if we were to actually look at that graphically, let me look at that graphically. I'm gonna plot the function, and it should be 3.1416. Let me do that. Cosmos. So I have a function x minus pi q. And there we go. There's the root. Stops there. Where is this? Pi. And what's pi? 3.14159, right? So our iteration method worked, right? Because we're doing it again and again until we reach the root. And that's called the bisection method, right? Okay, let me share back to my screen here. So that's the idea of the bisection method. It's that idea of going through it again and again until we reach some number approximately. We're not gonna get the exact value, but we're gonna get a numerical approximation using that method. And so, well, when we ended it, we ended up with, I think was a 3.1416. Well, if you look at the actual number of pi, it goes from like 159, what was it? Yeah, 3.14159.265 whatever. So my idea is that, well, it hasn't reached that exact value of pi. It's still quite far from it. So when we're storing that, so that's where the error is, that 2 to the power of negative p. That's the error because it hasn't gotten the exact value. So when we store that error of 2 to the negative p, it's pretty low, right? It's pretty low. And maybe there might be a better method. And of course there is. So what if at an initial guess x naught, we linearize the function f around x naught? So let's try another method. So what if we take an initial guess? So let's say x naught. And we linearize that. Our function f around that value. So around x naught. So what if we do that? Yeah, this is a new method that we're going to talk about. Just a heads up. So let's do that. Let's make our line. This is a function, L of x. We plot, or we plug in our x naught to our function. We add it to its derivative. So a calculus thing. X minus x naught. So here you can see this is a line. This is a line function. And then from there, we can find the root, right? So here we can find the root of my line function. And so what is this? Well, this is f of x naught plus f x naught x naught x minus x naught is equal to 0. right? And then we can do some algebra. We get this, right? I subtracted my f of x naught to both sides. And then what do I do? I forgot to add the tilde. That's the one we're trying to look for. I just realized. And then from there, well, we have this. So more algebra stuff. And then there we have it. So my x tilde is x naught minus this guy. And so that's the algebra behind finding this root. And so this root of the linearization might be a good approximation of the root, right? Because maybe this x tilde can serve as a new guess. And therefore an iterative method is created. So again, we can iterate through this, right? So if we remember from our previous lesson on iteration schemes, we can just use the Jacobi iteration. Xj minus. Right? And then we note here that, let's do a quick note. This should not be 0, or else it will be undefined. Yeah, this won't work if my denominator, my f prime, is 0. And so this method is a go-to if you have information on your derivative. And what do we call this? There's a particular method. So the first one was bisection. This is called the Newton-Raphson method. Right? And I spelled Rhapsody wrong because I was thinking of Bohemian Rhapsody. Anyway, and well, what if we don't have our derivative? Well, we can approximate it using our previous iteration, right? And this is, or this can be used if we know our derivative, f prime. Well, if we don't know f prime, uh, that's an issue. We can just simply approximate it using a previous iteration, right? So we can just do that. So how do we approximate this? So let's do this. And this is approximately our limit. Or no, that's not an approximation because we're getting the limit as x approaches my xj value, f of x minus f of xj. So here we're just doing slopes, right? And so now there's the approximation. J plus 1, I'm kidding, minus 1. And we're going to subtract that too. for that, right? So at the end of the day, we're just approximating. If we don't know our f prime, we just approximate it. Um, yeah, pretty much. Okay. Honestly, this goes both ways. I could put this first, but it doesn't matter. Any of them work. Yeah, this is good. And so what is this? Well, if we remember from our calculus, if we, this is a calculus one idea, but when we're taking the limit of something, well, what do we start? We're finding the tangent line, but we start with a secant line. And so, well, apparently mathematicians are not so original. They decided to just name this the secant method. That's funny. Yeah. And from there, well, here's the new iteration using the secant method. So we have our xj. And instead of us finding this derivative, well, we just say xj minus xj minus 1 minus xj over f of xj minus 1 minus f of xj. So this is a secant method, and we multiply it to this guy, f of xj, right? So we completely replaced this with its derivative. That's what happened. Um, yeah. And here, well, we have a condition, obviously. So the only condition that we have here is that my f of xj minus 1 should not be equal to f of xj. Because if they are equal, then it would be undefined again. So this thing shouldn't be equal, or else it would be undefined. And yeah, those are the three methods for finding roots. I might do, depends, but I think, or I'm thinking of doing a Python version of this, um, just to see how we can find roots. Um, but yeah, I hope you guys enjoyed and learned a lot. This one's a really interesting topic. I find this week's topic very interesting on interpolations of functions, on least squares or curve fitting, and lastly on root finding. So here it's all about, well, now we're interacting with the data, right? And this is something that I think is interesting when doing data science is that we're going to use mathematical methods in order to analyze and work with data and, well, get some insights, invaluable insights out of it. But yeah, I hope you guys enjoyed, really. I'm not that good of a teacher, but yeah, again, I'm just doing this because I want to document my learning. Um, and yeah, hope you guys enjoyed. I hope you learned a lot, and I'll see you all in the next video.